Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we're pleased you have joined us for today's presentation, Blame the Corona Treater, the truth about watt density, adhesion, and Dyne levels. This webinar presentation will be very unique, but more on that later. If you have a question, you may ask it at any time during the webinar by using the GoToWebinar question tool. We will reserve time at the end of the presentation to answer your questions. The presentation is being recorded, and you will receive access to the recording as soon as it is posted online, which is usually within 24 hours. During today's webinar, we will hit on a number of topics that you may want to take a deeper dive on. All of our webinars are archived on our website, and you can choose some topics such as installation best practices, corona treating maintenance, why all films don't treat the same, as well as many application-specific webinars. We're fortunate today to have two presenters who are experts in the field of corona treatment. Tom Gilbertson is Enercon's Vice President of Application Engineering and has nearly 30 years of surface treating application experience. Tom is a frequent presenter at industry events and has written numerous technical articles on the topic. Todd Krupa is Enercon's National Sales Manager, whose experience includes working with OEMs, brand owners, and operations to achieve optimal surface treating results. Tom, why don't you tell us a little bit about the topics we'll be covering today?
Thanks, Mark. And also thanks for making me younger. You just chopped 5 years off my age, and I really appreciate that. Welcome, everybody. It's great to have you. A lot of you have joined us in the past, and we really appreciate you attending the webinar today. So today we're going to talk about some key things relating to blame the corona treater. First of all, we're going to talk about knowing the facts of your application. You know, it's important that you understand what you're into at that time, and you'll see how this develops as we go through today's presentation. Watt densities, Dyne levels, and those relationships between those common issues. Various application issues that come up during the course of any converting or blown film day. Dyne levels, let's talk about dynes, right? We got to talk about that and get an understanding of really what goes on there and what that all means and how to actually do a dyne test. And then when things do go wrong, what's the question you ask? What's the number one thing you want to know? Well, of course, that question is, what's changed? So, of course, when things go wrong, and things always go wrong, everyone wishes there was some kind of easy button when there are wetting problems or application problems. And blaming a corona treater is certainly an easy thing to do, that's for sure. But as we all know, in the real world and day-to-day, problems are often far more complex. As I've said to many of you in the past, when we talked about application problems, it's very rare to have one thing solve an application problem. So the purpose of today's webinar is to make sure you have a better understanding of the relationship between corona, watt density, Dyne level, wetting, adhesion, and all those interrelated subjects, and then give you these strategies you can use day to day in your dealings with your plant personnel. Mark?
Thanks, Tom. As mentioned earlier, this webinar will be unique. Instead of the traditional approach of subject matter experts lecturing on best practices, we're going to tell this in a story format. We're inviting you to imagine you work for a fictional company called Acme Converting Enterprises. We're going to take you inside their operation in Arcadia, Indiana, where the company has recently landed a new customer and are finishing up a flexible packaging print job on polypropylene. It's Friday afternoon at 3 p.m. Let's listen in as production manager Phil Hammond is closing out his work week and looking forward to getting out of work on time for a weekend fishing trip with his family. That's when his phone rings, and it's Peter Pincher, the company's Chief Financial Officer and Purchasing Manager.
Hello?
Phil, how's the new job coming?
So far, so good. We're right on schedule.
Good. I don't need to remind you, we need to make this delivery on time. This can mean a lot for our company. Stay on it and keep me updated.
You got it. Oh, looks like Bob Blamerson is calling me from the shop floor. Let me take this call. Hey, Bob, what's up?
We got problems. I'm running that polypropylene job, and we're having issues with the ink. It doesn't look right. I'm thinking the corona treater isn't working.
Okay, Bob, I'll be right down to take a look.
As Phil makes his way out to the production floor, he thinks back to the training he received from Enercon and what he had learned about corona treaters. For the benefit of our audience today, Tom, could you review what Phil learned during his training with Enercon?
Absolutely, Mark. Thank you. So to get everybody sort of on the same page here, we're going to look at what corona treaters are and what they do. So if we go to the next slide, we can look simply at a corona treater as just a big capacitor. And without respect to the brand of the corona treater or whether it's a metal electrode or ceramic electrode, functionally and schematically, they are the same. So basically, a corona treater is nothing more than two capacitor plates with an insulator somewhere. In this case, we have the insulator in the middle. So between those two plates is an air gap of 60 thousandths, and corona is formed in there, and corona just being ionized air. So we take 10,000 volts at 20 to 30 kilohertz, we ionize the air between that electrode and the grounded roller, and we get corona. Now you're looking at it from a little different viewpoint. We can see the components of a corona treater system, and they include a power supply that takes the utility from the plant. We use that utility, we drop it to a high voltage transformer that boosts the power up to 10,000 volts, apply that to an electrode. The one we have shown here happens to be a segmented metal electrode, but again, doesn't matter, it can be affixed with electrode too. And that 60 thousandths air gap is right between that electrode and the surface of the roll, just like in the last slide. And in that gap, we get ionized air or corona, thereby treating that film. Corona treaters, very popular. Many of you guys use them. What do they do, right? We hear this question all the time. It's magic. It's a black box. Well, not really. The ionized air that we generate, it oxidizes the film surface. It forms low molecular sites on the film surface. It cleans the film surface. So many times we're dealing with films that have a lot of additives, slip additives, anti-blocks, colorants, maybe fire retardants, what have you. And all those things that are sitting on that surface can have a negative impact relative to wetting liquids. And remember, corona treater's number one job is to get the surface of the film to be receptive to wetting a liquid, whether the liquid's an adhesive, an ink, a coating, whatever. That's what the corona treater's main job is to clean that surface. It polarizes the surface, gets it functional, and then allows an ink coating adhesive to wet. So in this slide, you can kind of see what we're talking about here. So if you follow down the images there, we have an AFM of a polypropylene film, and in the A, we have no surface treatment on that at all. So the surface looks fairly benign. And as you go up in watt density, meaning you go higher in power, you can see that the changes on the surface of that material are drastically different, meaning we have more surface area there. We've created more surface area for an ink, a coating, an adhesive, for example, to grab onto and to wet. So in this image, you can actually see what the corona treater is doing as you go up in power. So what happens when you go up in power? How does that all jive with the corona treater? Well, everybody in the industry, anybody who makes corona treaters, they all size their equipment and determine the size of the equipment by calculating the watt density. Now, I've sat through enough presentations in my career to know that talking about formulas on a presentation are tough, and I'm not going to drag you through this step by step. But suffice it to say that all treaters are sized using this watt density calculation. And as we go through today, I'm going to ask you guys to consider, if you're not doing it already, to use this watt density calculation as one tool in your arsenal to tighten down your process control and make sure you're more consistent going day to day. And if you look at this image here, you can see that the calculation isn't difficult. Basically, you're taking the power level, the line speed, and the electrode width, and you're calculating these up, and you're dividing it, and you're going to come up with a watt density calculation. So to keep it simple, look at it this way. Let's say you had a 1-foot web, and you're running 10 feet a minute, and you're only treating one side. That's 10 square feet a minute. And if you're going to run at a watt density of 2, 10 times 2 is 20 watts. So you'd be running 20 watts at a watt density of 2. And if you think about that and you go through this calculation with your own details, your own application details in your shop, you'll find that this can be very helpful going forward. And we'll illustrate this as we go ahead. I'm getting a bit ahead of myself. But in any event, here's a great slide that illustrates this in the same way. And we're going to cover this same formula here going forward. But take a look at what we've got here. You got a 5,000 watt or 5 kilowatt power supply, a 5-foot electrode. We're running 100 feet a minute one side. That's a watt density of 10. In the other example, we increase the line speed by 5, by a function of 5. So that cuts the watt density in half, or more than half, actually. So you can see here you have watt density of 2. Now, many of you out there might say, well, this is great. Watt density of 2, watt density of 10, you know, whatever. Give me some context here. You know, what does this mean to me? Generally speaking, most corona treaters are sized between a watt density of 2 and 3. So you'll see as we go forward here, and if you calculate on one of your own applications, you'll likely see a similar number, and you'll get the position of where we're at. Generally speaking, higher watt densities produce higher Dyne levels, generally speaking. But again, we'll be dealing more with the details of this as we go along. Finally, in this part of the presentation, one cautionary note. You cannot use a watt density to predict the Dyne number. And you might ask, you're probably thinking now, well, I wonder why that is. You know, why don't these things just kind of linearly march with each other? So if in one instance, on one polypropylene film, I might get a watt density of 2 and get 40 Dynes. And I run another polypropylene film at the same watt density, I don't get 40 Dynes, I get something else. And why is that? We must have to blame the corona treater for that. Well, maybe and maybe not, but we'll get into this as we go forward. But please remember, you can't use a watt density to try to predict Dyne numbers. Mark? Oh, one more slide, sorry. So why is that? Why is that? Why is it that my example where we got 40 Dynes in one instance and we don't get 40 Dynes in the other instance? Well, here's a good reason. I forgot we had the slide here. So if you look at this slide, you can see all those little baggage items on the web before it goes into the corona treater. And really, that's what we're talking about. What baggage is your film bringing to the treater? So let's take two extreme examples here. We'll have a polyethylene film. We'll have just a virgin polyethylene film in one example, and then we'll have a polyethylene film that has a high slip content and a bunch of anti-block. Now, if you're not aware of these details, and all you looked at and all you were paying attention to is the film's polyethylene, that's all you were paying attention to. And you had a job, you put the job up on the press, and you're running these two jobs, and you weren't paying attention to the differences between those two films, it's very understandable why in one case you'd be successful at a given corona treater setting, while at the next case with the same setting, you would totally not be successful. And that's because of the baggage that's coming along with that other film. So it's really important to understand the film that's being fed into the corona treater, what's on it, what's in it, what's happening to it, and then operate it appropriately. Now it's your turn, Mark.
All right, thanks, Tom. So let's go back to the Acme production floor and see what's going on with Phil and Bob.
See, Phil, the printing doesn't look good. Got to be the corona treater.
Did you check the ink chemistry, the analox rolls in the dryer?
Yes, it all looks good. I'm telling you, it must be the corona treater.
Well, the ink's not wetting out, that's for sure. Let's double check our corona treater recipe for this application.
Okay. Well, as we know, the application is water-based printing.
Mm-hmm.
We're using pre-treated 1 mil polypropylene, treating one side 60 inches wide.
Okay.
Line speed of 500 feet per minute.
All right.
5 kilowatt power supply with a 2 watt density.
All right, that all checks out.
Told you, it must be the corona treater.
Maybe, maybe not. If it's a treater, it should be easy enough to detect. Let's do a quick audit.
During a recent courtesy visit from Enercon, Bob had received training on key areas to look at when auditing the setup of a corona treater. Todd, could you review the areas a press operator like Bob should be able to inspect?
Sure thing, Mark. So one of the first things that you want to look at here is do a visual inspection of the treater in operation. Can we see and confirm that the treater is actually on and running? If it's accessible, you should be able to see the haze of the corona being discharged there. And if you certainly can see the discharge, you want to check to see if the treater is fully running across the web. And we will get into that a little bit deeper here in the presentation as well. But we want to check it to see, is the treater on? Now, the displays will certainly give you a visual inspection as well. It should tell you, are you running in operation here? Do they show you that the unit is going through any faults at the current moment as well? You can see on the right in the picture where it has all the green lit up buttons for the exhaust, external, electrode, and the minimum speed, and that it is in a running state and is ready to go. So that will give you another visual inspection that the treater is on and in operation. Now, for the treater to be in an operational state, it does need to have its safety interlocks met. Without all these safety interlocks met, it's not gonna operate. And of course, we want to make sure that everything is safe and ready to go for you. It's going to give you different feedbacks, and the main interlocks for each of the treaters that are out there is going to be your roller, your ground roll. Is that in operation? Is it moving? Is the web moving through the treater at the time? And is it at its minimum speed? It's possible that your treater is not kicked on at the minimum speed of the line that you've set it at. You'll also have an exhaust interlock, which will tell you if your airflow is moving, and we will get into a little bit more detail on that. But exhaust is an extremely important part of the treater, and if it's not moving through the electrodes, you're going to get an interlock fault, and you won't be able to operate the treater. Lastly, two other things is the electrode assembly. Is the electrode assembly in its correct position? Did it return to its position after it was opened up for various reasons, or was it not pushed all the way in, or was it jammed for any reason? Those are some key indicators that your electrode might not be in position. It'll tell you right on the station. Lastly, there is an external interlock that most treaters will have. You'll be able to lock that into your line, and so it'll tell you if anything from an e-stop perspective or anything that's in your line that you have sent a signal to the treater saying don't run. So you want to make sure that each of those interlocks are met appropriately. So safety first, though. Now, if we do see that the treater is running and everything is going well, great. Then we can look into some application data on there. If it's not running, we want to double check a few things. So safety first, follow your lockout, tagout procedures here to disconnect the power from the treater before getting your hands on and maintaining the treater. Also, you want to make sure that the treater is properly grounded, so there's not going to be any shorts or anything that could cause some issues there. Now, what we want you to do is check the gap of the electrode. Gapping is very important for the treater's performance, and as Tom mentioned earlier, we want to make sure that we're at a 60,000th of an inch gap. It's 0.06 inches, and that's maintained across the web of the treatment. And if there is any uneven treatment or uneven gaps, we want to make sure that that is adjusted and corrected on that time.
So Todd, in this case, the one element here, folks, that we want you also to be aware of and why this gap is so important, and a key takeaway I want you to remember here, the corona will always go to the path of least electrical resistance. So in Todd's slide here, if we were to make that electrode such that the far end of the electrode was close to the treater roll and where that gap gauge is further away from the treater roll, it's not that the treater won't work. It'll operate just fine. But all that 5 kilowatts that we were just referring to, it's going to want to go to the closest end of the electrode to the treater roll. And so what does that mean to you practically? Well, that means that when treating that web, your dyne level likely is not going to be uniform. And that's because you got all the power trying to go to one end of the electrode assembly versus the other. And then the final thought on that is if that is the case, that stresses that all that power dissipation on the far end of that electrode assembly stresses those components if it's left in that condition. So not only are you getting uneven treatment, but now you're also stressing the various electrical components and insulators on that end of the treater and causing them to potentially fail sooner rather than later. Todd?
Great points, Tom. Thank you for that. So 2 things that your treater absolutely needs to maintain and to be aware of is airflow and cleanliness. And airflow is going to be one of the most important parts of maintaining the treater. It does aid in maintenance as well. A byproduct of corona treatment is going to be ozone creation. And ozone, we don't want that near our operators in the vicinity of the operation of the unit or anywhere in the general area there. So we want to exhaust that out. And the best way to exhaust that out is through the electrode assemblies and into the aluminum exhaust tube and then outside the building or into a decomposer of sorts. And while we're pulling this airflow, it's doing the other side is cooling the electrodes. And you can see that the airflow around the electrodes goes around them and through them into the exhaust tube. And by doing so, it keeps them cool. And keeping those electrodes cool is going to give them longer life and better operation and better durability for your operation.
And keep in mind, folks, ozone is heavier than air. So the reason that air gap is like that, one of the reasons, I mean, there's multiple, but we are grabbing that O3 molecule right at the generation point of the corona. We're not allowing it to escape. Some of you are old guys like me, and you'll remember in the day, corona treaters had big boxes and covers around them. And the purpose of those at the day was to try to grab that O3 molecule and contain it. And of course, it never did, right? The ozone leaked out of that old box. And not only did it get into the shop floor, but it caused the box to rust and be just ugly and bad to work with, right? So now we grab that molecule. We don't rely on a box to try to capture it. Airflow grabs it, contains it, moves it through the system, and as Todd indicated, goes into the exhaust system, decomposer or not, whatever your requirements are, and then out of the building.
Thank you, Tom. Here's a few visual examples of problems with neglected stations. So again, something pretty simple. Light maintenance would likely have caught these issues earlier on if in the process there. But you can see the ground roll is pretty dirty, pretty damaged up. Again, it's going to give you poor treatment, possibly roll covering failures. Contamination on that web is even causing backside treatment, which Tom will get into in a little bit as well. On the right, the electrodes, you can see that you're just going to have electrode failures and need to repurchase any of those spare parts to maintain your treater and keep them going. But you'll get the high voltage arcing, and that could just be an issue safety-wise and for production. The ground brush here is something pretty small and pretty simple, but it's very key that you guys maintain and make sure that you're aware that this little brush here, this little carbon brush, is in contact with the ground roll. Like it says on the slide, if it's not in contact with the roll, you'll certainly see the corona, but it might not treat as expected. And what that means is that the discharge will go, instead of through the ground roll where you want it to, it'll go through the bearings of the system. And that can cause your ground roll to seize up, the bearings to get worn out, and have to replace all those. So it's a small little item, but make sure you're keeping track of replacing that ground brush and just keeping an eye on that over time. Lastly, you want to check for inspecting for arcing. Arcing is simply that, where Tom mentioned, it's going to be looking for the easiest path to ground. When it is found, it'll certainly arc to that, and rather than the ground roll where you want it to go. Carbon tracking is one of the visual inspections of an arc, high voltage arc, and it can be caused by dirt buildup, damage to the electrode components, or excessive moisture in the air. It can occur at the electro mounting tabs, the insulating shroud, the mounting block, or even the high voltage wiring. Lastly, other areas to check. Again, with the treater roll and material speed, make sure that your roll is turning with the material speed as it's going through. If there is any drag there, that can be causing some treatment issues. You want to make sure that the roll is free spinning with that, or if it is driven, that it is driven at the right speed. And then look for any wrinkling or film puckering as it's going through the treater. If you can get a visual of it going through and it is making intimate contact with the roll, then you're going to be in the best position for success.
All right, thanks, Todd. Let's check back in at Acme. Bob has completed his inspection and is reporting back to Phil.
Phil, everything looks good. I don't get it. It must be the treater.
Everything with the treater seems good. Hold on, Bob. It's Peter calling.
Bill, why's the line down? Time is money. We need to get that press up and running.
I know. We're on it.
You better be. We can't leave today until this gets resolved. Understood?
Understood. Bob, let's check the Dyne levels after the treatment.
So, Tom, while Bob checks the Dyne levels, what are some of the key things converters should keep in mind regarding Dyne levels?
Well, Mark, the Dyne levels are an important aspect of our business. All of you out there have done this test and have had your own experiences relative to Dynes for a long time. Basically, what the Dyne test is doing is it's giving you an understanding of what is the surface of the film's ability to wet a liquid. Dyne solutions are made up of two solvents, and they're ratioed in a certain proportion to each other, and that will then allow the solvent to be a 36 Dyne, a 38 Dyne, a 30 Dyne, a 50 Dyne, whatever the number is on that bottle. Think of Dyne level like your blood pressure, right? It's just an indicator of your chance of success relative to converting. Just like your blood pressure is an indicator of your health, right? You can have really good blood pressure, but if you have something else wrong, the blood pressure isn't going to necessarily indicate that, but it gives you just a general feeling of where you are. Dyne level is like that. You can have, and many of you probably have had this experience, where you do a Dyne test and you look at the result and you say it's 42 Dynes, but this ink looks terrible. How is that possible? What's going on here? And it gets very confusing. Well, part of the confusion there is because we have a lot of moving parts at once in the converting process, right? When we're printing, there's all kinds of stuff going on at one time. Let aside for the fact that the Dyne test, as we all know, has its own problems, right? It's a subjective test. It's not easy to do, let alone is it easy to replicate and be consistent with. So one of the ways I would suggest, and if any of you want this document, just reach out to me through email after the presentation. I'll send it to you. We're kind of making a big circle here. We'll go back in time relative to how to do a Dyne test. The first image on the left you see really isn't incorrect. What it is it's a typical Dyne marking that you get when using a pen. How many of you out there have seen this? And I can just see everybody raise their hand. Yeah, thank you. This is very common, right? You take a Dyne marker and you go out there and you run the Dyne marker across the web, and now you're trying to determine whether that number is 40, is it 42, is it 38, what is it? And you have this tiny little, if you're lucky, eighth of an inch, 1 inch long or something, image that you've marked up on there, and you try to figure out from that. And let's all be honest about this, that test method is not a test method. It's a great method if you're trying to figure out what side of the film is treated when you're loading up a new roll on the line. That's fine. But if you're really trying to figure out what the Dyne level is, that's not going to be very consistent or very accurate. Rather, what I'd suggest you guys use is go back to a method that has been used for a long time, using a Meyer rod and assortment of Dyne solutions. So for example, in this case, we have a sheet of film, and let's just assume the sheet of film is 42 Dynes. So we put a drop of 40, a drop of 42, and a drop of 44. And we take that Meyer rod and we draw it down all three at the same time. We wait our 2 seconds, and we can see these images populate right in front of us. So right here and now, you've got 3 data points that you're comparing side by side right now. You don't have to remember what the last one was. Because of the Meyer rod, you don't have to worry about, visually, you don't have to worry because you get a big swath of Dyne solution down there. You can easily see what the results are. And then finally, this test is repeatable. So long as you're using the same Meyer rod and you clean it off with some alcohol in between test runs, you're good. Your test data that you collect should be good going forward. Now, the downside of this test is, admittedly, it's not convenient to use this at the side of the press. And I understand that. That is a downfall here. However, if you combine this test with a marker test, and then you run those 2 data points, I think you'll find going forward, your end results are going to be far more consistent and reliable to work with. I have a technical paper on this that Tappy did a long time ago. If you're interested in it, I'll be happy to send it to you later on today. And really, what are we trying to overcome here? What are we trying to get away from? And again, this is something you guys all have seen. You're experiencing it yourself. We all have different people doing this test. Everybody's got their own methodology relative to doing Dynes, particularly when you have a marker. And they're all well-intended. Everybody's just trying to do their job and do it correctly. But because the variabilities in the test being what they are, and frankly, the variability of just using a Dyne pen, you get all these various readings. And so it's hard to get your mind around it. Now, so long as the machine's running and you're producing good material, nobody really worries about it. It's really what happens, as you're going to see going forward at Acme Converting, it's really what happens when things don't go right and the data you have is kind of convoluted and not consistent. So when you run these Dyne tests, you want to run them on film samples that are you're using for your application, and you want to use the Meyer rod test method. If you use things like contact angle or these other technologies out there, that's fine. But those technologies, first of all, don't give you really a Dyne number. They give you a contact angle number, and that's okay. You can record that data, but it doesn't correlate directly to a Dyne number. Secondarily, when you talk about those contact angle devices, they are very accurate, but they are only measuring like 1 square inch of the material. All of us out there know that in the real world, we're dealing with 5 foot wide, 6, 7, 8 foot wide webs. So it doesn't matter if a 1 inch square area looks good. You need to know how it looks across the web width. And so those devices really aren't suitable to tell you that. Doing a Meyer rod test on that material, because you can spread the solution out over a wide width rather, is much better, and you're able to actually ascertain something. One other final note on that, doing a Meyer rod test. For any of you folks out there that have had experience with or suspect backside treatment issues, and you're trying to figure out if that actually happens, or you're in the middle of that and you have a concern, flip a sample over, take the side you suspect to have backside treatment, and if you know the inherent Dyne level of that material is supposed to be, say, 30 dynes, take some 32 or 34 Dyne and a Meyer rod and spread it out on the back of that sheet. And if there's backside treatment back there of that sufficient amount, you will see a pattern show up. That pattern can then direct you to maybe a cause to remedy that problem. Again, we did a technical paper that featured some of that information on it many years ago. And again, after this presentation in the future, if you want to have a copy of that, we can send that over to you. And remember, finally, the Dyne level does not guarantee adhesion. Dyne level is simply measuring the surface's ability to wet a liquid. That's it. That's all the Dyne level is doing. And so you have to remember that. Mark? Oh, yeah, we did cover it's a good point here. I always forget about the side of this that I kind of lose track of because I make assumptions that everybody just uses fresh Dyne solution. Some of you out there have asked me this question when I visited with you. You'll say, well, how long are pens good for? Or where should I keep these bottles of Dyne solution? Or when should I change the bottles of Dyne solution is a really common question. The answer to that is, generally speaking, in bottles of Dyne solution, generally people like to turn them over in 6 months' time, and that's assuming the solution is kept in a cabinet. It's not just left out in the open. Remember, the solutions are made up of 2 solvents, and the solvents will evaporate. So if you leave the cap off the bottle, you're going to now screw up the ratio of the 2 solvents that then equal a certain Dyne number. And as that happens, that Dyne solution now is not accurate. It's not valuable anymore, really. So if you are a little lax relative to storing and handling the Dyne solutions, you may want to change them more often than 6 months. But generally speaking, 6 months tends to be the deal there, and you want to kind of keep that in mind going forward. And again, keep in mind, use that ASTM guideline relative to the Dyne level testing. If you have questions on that, you can certainly reach out to us in the past, after the presentation is over. Another question that comes up quite often is backside treatment, and what is it, and how do we get rid of it? And it's a topic that gets sort of chewed on a lot, and a lot of times it's simply because it's just not a topic that people fully understand, but yet at the same time it's a very simple problem. Corona is nothing more than ionized air, and you remember we talked about that a few slides ago. So if I get air underneath the web, as Mark's illustrating here, where you get a wrinkle in the sheet, or maybe the web tension just isn't very good, for whatever reason, air gets underneath there, you're going to get corona back there. Now, in and of itself, that doesn't necessarily mean you're going to have a failure or there's something terrible going to happen. It also depends on what the material is. So let me give you two examples. If I'm getting backside treatment with polyethylene, it's easy to treat. Then if you do a backside treatment test, likely you're going to see an increase in Dyne number back there. Why? Well, because it's easy to treat. And so even a small amount of corona on the back of that web is likely going to give you some kind of increase in Dyne number. Now, that again doesn't necessarily mean an emergency or a trouble. It just depends on what that number is and how much is back there. With the same application, the same air, the same power, if I ran a polypropylene film, because that's harder to treat, you might not notice anything. You might get backside treatment, technically, you get corona back there, but it doesn't really do anything. So really, again, you know, measuring, watching, Todd said it perfectly, web path, web handling, making sure you don't get wrinkles or bags or baggy edges going through the treater. Anything like that that goes through the treater where air gets underneath the web, you're likely going to get ionized air back there, and it's going to, you know, potentially cause backside treatment. If you have it, what is the corrective action? Well, if you have an existing treater, the corrective action is really kind of simple, and that is you're going to have to run a little more web tension on that web if you can to try to flatten that web out on the surface. Going forward, if it's a consistent problem and you can't remedy it by changing film or, you know, talking to your film supplier and seeing if they can get you some better product, then you may have to look at some pretty drastic things like adding nip rolls, driving the treater roll, maybe even adding some additional accessory rollers like grooved rollers or things of that nature. But really, you really want to make sure that these wrinkles or the cause of the backside treatment, how you got the air back there, is really where the remedy's got to come. And usually it's as a result of things like Todd's slide comes to mind now with the dirty treater roll, and that's an easy thing, right? You can clean that and get that remedy. Low web tension, make sure your film is running properly through the treater. And of course, in some cases, if you're running some baggy film and you have to, you don't have a choice, it's just the nature of what that job is, it may mean that, you know, in order to get through that job, you just have to run the line a little slower. And I know you don't want to do that. We don't want you to do it either. But sometimes the reality just forces the situation such that it is. So those are the remedies that you can take if you have a particular issue of backside treatment.
All right, thanks, Tom. So Bob has completed his Dyne test at Acme. Let's see if he and Phil have figured out the problem with the printing issues.
Phil, these Dyne levels are pretty low. We should be seeing 42 Dynes.
All right, let's lower the line speed a little and see what Dyne results we get.
Way ahead of you. I tried that, and at 300 feet per minute, the Dyne level looks good.
Okay, then let's try printing at 300 feet per minute and see what happens.
You got it.
Bob runs the press at the lower speeds.
Phil, you're a genius. The printing looks great.
Interesting. That means the treater is affecting the film, just not at the rate we've seen before. What else could have changed?
Been running fine all week. I came in today, threw up the film, and boom, all heck breaks loose.
Hold on, this started with this roll of film?
Yeah, it was one of those rolls that came in yesterday. Peter got a deal from that converting operation that went out of business 6 months ago. I used to work there, and man, they never took care of their equipment. Always had a lot of downtime.
All right, did you check the Dyne level on this roll before we started treating it?
No, let me check. Should be 34, 36 Dyne. Hey, Phil, it's only 30 Dynes.
Got it. How many rolls of this new film do we have anyway?
About 4. Why?
Okay, let's continue to run the press at 300 when you use that film. And remember to check the film's Dyne level before each run. With the time we saved earlier in the week, we'll still be able to make our deadline.
You got it. Hey, aren't you going on a fishing trip this weekend?
Yeah, and I think I'm just going to make it out on time. I've got to let Peter know that we're up and running. When you finish the job, make sure we take time to maintain the treater and the rest of the press.
Sounds great. Have a good one.
Peter, it's Phil. The line is up and running, but we had to slow down to 300 feet per minute, but we'll get this out on time.
Great news, but why are we slowing down?
Well, it's that cheap film you bought. The initial Dyne level was really low. Not sure if it's the additives, the age of the film, or what, but we were able to get it to work. We need to be careful in the future when working with new materials. I'm just glad I had that training from Enercon, and it really helped.
Nice work, Phil. Now get out of here and go catch that big one.
Will do. See you on Monday. Fish on.
All right, so a happy ending for our friends at Acme Converting Enterprises as Phil saves the day by applying his knowledge of corona treating to solve their printing issues. We're going to open it up to questions in just a moment, but first, Tom, can you double back and review some of the key takeaways from today's presentation?
Absolutely, Mark. Well, I think the number one thing we all can get from this little podcast play here is know your facts, know your application facts, understand what's happening in front of you. Make sure you understand things like what condition is the film in, what dyne level is it at, what am I doing with this particular product. Also, watt density is the best way to measure applied treatment, right? Not necessarily dynes. Think about the power of this, folks. If you actually measured the dyne level, recorded the watt density, both, I should say the initial dyne level and the treated dyne level, and the watt density, and you line those up, and then you also measured, like in this case, the adhesion and the appearance of that ink on that job, and you put a check mark that said, we're great. And you do that every time you run that job, and you continue tracking those key elements of the process. Going forward, if you run into a problem, as illustrated here, you'd have some solid information that you can go back on and then help yourself troubleshoot. Additionally, dyne level doesn't guarantee adhesion, and as you guys know, it does decay over time. So when you're buying film from some other place, you can certainly expect that as that film ages and things change with it as it's sitting in storage, that dyne level is going to be different than maybe what you expect. So as we know from our friends at Acme, it's really important to test the dyne level of the film prior to you putting it up on the line. And then let's not discount the maintaining the treater. You know, Todd had a great number of slides there showing, you know, what happens when the treater roll looks pretty ugly, hasn't been cleaned for a while. What are the ramifications of that? What happens when you get high voltage arcing on your electrode assembly and you don't clean it properly? All those things affect this process job as we go forward. And really, when you are presented with these sort of weird results, things you didn't expect, what do you got to do? Well, number one, check your application specifications. Are you running the job the way you ran it last time? If you're not, why? What changed? Verify your treater setup. Make sure it's running in the condition and the way you wanted it to run on this job. Always test your dyne level. What's going on there with that material? And then finally, if you still don't come up with an answer, simple question, what changed?
All right, thanks, Tom. I wanted to just remind everyone that in addition to the recording of today's presentation, you'll also receive access to the following: our surface treating handbook filled with best practices, a worksheet to document each of your applications, just as Tom indicated you should do. And also, we'll send you out a link to our online watt density calculator. We're going to get to your questions. We're just going to ask one question of you before we move forward in the form of a poll. I'm going to go ahead and launch that poll right now. If you could be so kind to provide us with an answer, we would appreciate it. All right, looks like we've got about 3/4 of the vote in. We'll give it a few more seconds. All right, appreciate that feedback, and hopefully you've enjoyed today's presentation. And we're going to move on now to your questions. Again, you can use the GoToWebinar toolbar for that purpose. First question is, how much moisture is excessive moisture when it comes to corona treating?
Well, that's a great question. I've never had anybody, this is Tom, I've never had anybody ask me that question before. Let me just put it to you this way. If you actually have, or if you have condensation, or you can actually see moisture on the treater roll, on the web, in the electrode assembly, things of that nature, or concurrently, if in that condition you're seeing the corona or getting the experience where you're seeing high voltage arcing in that condition where the treater's not staying on, it'll arc to that water, that I guess would be very way too much, right? So you want to make sure certainly nothing's visible. If you have a situation like in the summertime, maybe you're in a location that's very humid. Many people, what they do when they leave the treater over a weekend, maybe it hasn't been running for a while, they'll actually open it up and just dry it out. They'll take a little contact cleaner or some kind of alcohol, just dry that area out with that before they fire the treater up. And that may help in those conditions as well. So I hope that answered your question.
All right, here's a question. What should we take into account when running different thicknesses of polyethylene? For example, 1.5 to 4.5 mil.
Excellent question. Another one, we get this all the time. Really, for majority of converting applications, because the thicknesses of our products are really pretty minimal. You know, so the Corona treater doesn't care if the material is 0.5 mil or 4 mil. So that you really don't have to account for thickness in that way. Now, I will say this, if you're talking about going from, say, a traditional 1 mil product to all of a sudden you want to run 30 or 40 mil product, well, yeah, then you might have to take an action, and the action might simply be to increase the air gap, right? You have to make sure mechanically the substrate can get through the electrode assembly. But in terms of adjusting the power for that or those sorts of things, it typically doesn't matter. It's not something you have to worry about.
How critical is it that the exhaust flow meets or exceeds the recommended CFM?
Well, I know, Todd, how about you? I think it's pretty critical, don't you?
I would agree with that, Tom.
Yeah. I mean, here's what happens. If the exhaust flow specification is not met, both in terms of CFM and static pressure, the end result of that can mean, the worst end result of that can mean you get ozone in the operator area, and that's not acceptable. You just simply don't want that. So really the remedy there is to go back and look at your exhaust system, the size of your blower, make sure things there are to spec, you know, are operating like they need to. One other comment on that, if it's a newer installation, and this happens all the time, by the way, when they wire the blower up, make sure they wire it up so the fan's turning in the right direction. This happens where the mistake happens where they mix the wires up and the fan's rotating in the opposite direction. Of course, you're not getting any suction then. So it's a common occurrence that happens, but that's just a step to look at if you're in that situation.
We've got a customer that is going to be running polystyrene, and they haven't run it before. Can you speak towards its receptiveness to Corona treating?
Well, polystyrene, polystyrene. So if I go in the order from easy to hard in film and receptive to Corona, styrenics, nylons, and polyesters typically respond the easiest to a Corona treater. We used to have a joke around here years ago where we said on a roll of styrene, if you held a 2D flashlight on it long enough, you could get 72 dynes. And it was just a joke, but it just illustrates the point that styrenics are very easy to treat. So they don't take a lot of power. On the other end of that scale are polypropylenes, OPPs, BOPPs, things of that nature. They are harder to treat. And then really it's because of the makeup, the chemical nature and the makeup of the surface of those films. So I hope that answered your question out there.
What is the best between ceramic or silicone covered rolls?
Yeah, I'd like you guys to reconsider that topic and look at it differently. It's not good, better, best. I want you to think about your operation. So here's what I'm getting at. Do a reality check. How good are you guys at maintenance on your treaters? If you're really good at it and you have some diligence to it, I would say a ceramic roll is a great choice for you. And that's because it's going to give you good life. It's a hard covering. It can't get damaged by somebody digging it with a knife, anything like that. That'd be great. Let's say, on the other hand, your maintenance on the treater is maybe not perfect, all right? You're used to having sleeves. It's a common thing for you guys. Your culture that you have and how you deal with the treater every day is kind of into that mode. I'm not sure I would recommend to you to necessarily put a ceramic roll in there, not because it's not better, but it doesn't really fit with what you do. And so what happens there is an expectation is assumed. It's not met because somebody's not understanding how to maintain that roll or, you know, the various things around it. And then it fails prematurely and there's disappointment there. So I think, you know, you have to look at your process, how you guys work with the equipment, and then kind of determine it. If you look at it, if the topic is simply a topic about specifics or details, Dielectrics, like ceramic, have a very high dielectric strength, and they are tolerant of both heat, ozone, and corona, so they're very tolerant. Silicones, on the other hand, are decent at it, but less tolerant, and mechanically, they can be negatively affected just by with a razor knife or common things that, operators walk around with. So again, they're two different products. If you look at it strictly on the benefit of technical details, well, a ceramic roll is a winner every time. On the other hand, if you look at it and how your shop is, you may decide that actually silicone sleeves aren't so bad.
I've got a question. I think this goes back to the Acme converting example. Wanted to know if they could have also increased the power output to solve the problem instead of decreasing the line speed.
Well, let's put context on that. What they were trying to do there was identify where the problem was, right? We're trying to understand, is the problem with the film or is the problem with the corona treater? Because remember, in our example, the corona treater was giving them corona. They could see the corona. So it wasn't a question of, is it working? It's actually working. It's on. But now we're still not getting the results. So how do we determine that? Well, we turn the power supply to full rate, and we drop the line speed. And all of a sudden, we're successful. So what does that tell us? That tells us that the treater is working. It is doing what it's supposed to do, but this particular film just wasn't responding. And this little radio play we did here comes from real life, folks. This is an application scenario that happens all the time. And it's a common troubleshooting method that we will tell people to do when they're in a similar situation. So if they had latitude to raise the power further, you could have done that and left the speed the same. And that might have worked. It could have solved the problem. But really what you're trying to do there is figure out where the trouble is. Is the trouble with the film or is the trouble with the treater? And that's how we did it. And then, by the way, we can remedy it for the next few rolls and then get back to the rolls that were better and inspect and then deal with it from there. So that was the point of the test. But you could do it. You could certainly raise the power and see if that helped it too.
So we've got someone here who very much enjoyed the presentation and would like to learn a little bit more about temperature and things like increasing watt density. What implications of a temperature increase, more treatment, including the web behavior like wrinkling? Could you speak towards that?
Well, within the general context of watt density, so in other words, if we're running standard watt densities, let's just say the standard range is between, say, 2 and 3 watt density, okay? And if we're in that standard range, typically you're not going to see any heating of the web. The roll temperature in that treater is going to be, somewhere around 140, maybe 160 degrees F. So that's not anything that's going to affect the film in a negative way. It's not going to cause the film to pucker or wrinkle. You're not going to have any issues there. So if you're running kind of standard watt densities, you really don't, it's not going to affect the film in terms of a negative way. The film wrinkling and puckering most of the time comes from the film itself. The film got sent to you guys and it's got a bag in it or baggy edges or some kind of it's out of specification in some way. And you may not recognize it, of course, when you first put it up. You may not notice it. Maybe it doesn't even happen until you're in the middle of the roll or something. So the corona treater can only deal with what it sees. It's not an intelligent device. It doesn't know anything. It doesn't know that this roll of film's got a bag in it and the last one didn't. So the watt density really is just a manner of addressing or identifying how much power you're dissipating over a given speed and width. It doesn't necessarily mean anything relative to things like wrinkling and puckering. Those really are issues that are related to other things that are corollary issues to corona treatment.
All right. This person has a metal bar electrode on their corona treater. Is it possible to change it to a ceramic bar?
Technically, it's possible. It's a difficult question to answer because it's got a lot of moving parts to that question. It's a great question. Technically, it is possible, but the devil's in the details, and if you want to reach out to us offline, we can get into the details of those things.
There's a couple questions here. About maintenance, and do know that the surface treating handbook that we will be sending you guys access to will include best practices for the techniques that you should employ, as well as you can go online and look at our maintenance webinars, which gets into that very, very detailed. I have a question here. Have you seen film that has a highly pitted surface require different treat levels?
That is a great question. And not that it requires highly different treatment levels. I want you guys to think about this for a minute. So the questioner put this great thing out there about a pitted film. I'm going to twist that a little bit, and I'm going to also throw into that mix embossed films. Now, doing Dyne tests on any of these films that have a topography to them, I'm going to let you guys know right away, there is no consistent way to get consistent Dyne readings on a surface that's not flat. Okay? So if you look at the ASTM test method for doing Dyne tests, they're talking about non-porous flat film. Not film that have embossing in it or grooves in it or some sort of machining in it, whatever it is. And so what that means to you is it doesn't mean you can't do a Dyne test, but it means you're kind of going to be breaking your own ground with respect to the Dyne test method and your end result. Because there is no consistent way to read a Dyne number when the Dyne fluid is going in pits and valleys on the surface. So just be aware that, you know, it's not that you can't treat it, it's not that you can't do a Dyne test, but the results you get are even going to be more variable than commonly. So you just got to be mindful of that as you go forward and not lean too much. In that case, I wouldn't lean too much on these Dyne tests. If that product is being printed or coated or laminated, in that case, I would look more at wetting of the end result and adhesion of the end result, and I'd focus more on that along with the watt density number to help you guide yourself going forward.
I've got a question. Someone to improve the lamination, they use primer combined with corona treatment. Is that common?
Oh yeah, it is common. On extrusion coating machines, for example, it's very common. You unwind, you go through a primer station, you go through a corona treater, and you go into the extrudate. It's very, very common.
Can you speak to the differences in how long materials retain corona treatment over time?
Well, that's another great question. I think we actually also did a technical paper on that. There is no standard here. Everybody's material is different. And of course, it also matters how it was stored and where it's coming from. So let me give you a gross example. So we have a film extrusion department. They're blowing film. We get 42 dynes. It's got some slip in the film. And we take that, in one example, we take it out of the extrusion department. 3 hours later, it gets to converting, and we print it, and we're in good shape. The extreme example, opposite end of that, is take the same film. We put it out in this semi-trailer that's sitting out in the parking lot in the middle of summer, and the trailer's 140 or 160 degrees inside of it, and these rolls are just kind of sitting in there and cooking. The Dyne level retention in the latter is going to be a lot different than the Dyne level retention in the former. And so what am I telling you? I'm telling you that there is no standard there. It depends on the additive loading of the film, with the age of the film, how the film was stored and handled. That's really going to determine sort of the general principle. At the end of the day, if you're a converter, you want to buy quality film that's pre-treated, and you want to rotate that in your inventory in such a way that it doesn't sit out in a trailer for 3 months or something, such that you know when it comes in, when the film comes back into the plant, you're going to be able to do something with it.
We have a question on purchasing the tool to check for consistent gap measurement. The good news there is those are free from Enercon. So if you want to email Tom or Todd, we'll mail you a couple of those out that you can use in your operation. Tom, there's a couple questions about overtreatment. One is, how do you detect overtreatment? And I'm looking for, there's another one here. Oh, is overtreating of the film affecting the COF?
The topic of overtreatment is a little controversial. Let me just say this. It's difficult in a standard operation to overtreat the film. Now, I'm not saying you can't do it, but it's not typical. And ink failure, while it can happen on overtreated film, normally ink failure, adhesion failures aren't necessarily there because you overtreated the film, okay? It's there for other reasons. It's hard to actually pinpoint overtreatment in and of itself. How it was learned about years ago is actually through a scientific experiment where the test method was looking at some water-based printing, and they did some ESCA testing, and they could see an area of this substrate that had a lot of low molecular weight material on it that was printed on the surface of that material. When they did a tape test, the ink actually stuck to the top layer of that poly. But because of the amount of treatment in that instance, it created weak interfacial boundary layer between that treated surface and the surface below it, and the ink came off with the tape. And of course, you couldn't see it with your naked eye. You had to look through a piece of equipment to actually see that. So it's not that it doesn't happen, but it's really hard to over-treat film. You'd have to be running your power supply at a full output, let's say, and then running at some ridiculously low speed, which nobody's doing that because you can't make money doing that. So it's not impossible. It is there, but I wouldn't be real concerned about it.
Couple questions related to Dyne level. Generally speaking, is there a typical raise that you see in Dyne level after treatment? And what expectation of increasing watt density should we see after treating, say, at a Dyne of 36 to 38? So again, looks like trying to predict.
Yeah, hard to predict. I mean, really, if it's really impossible to predict. If I had to just to throw a dart at this and just based on experience of, if you have polyethylene film, for example, and it's coming to the press at 38 dynes, and you're running through the treater, it likely comes out of the treater at a watt density of 2. You might be in the low 40s. You know, it might be 42, 44, something like that is pretty common. Now, that doesn't mean it's always going to be that way. As our little play here was illustrative, sometimes, you know, the material changes in between. People don't realize that you've gone to a different batch or a different brand or something, and that brand or batch is not, you know, isn't reacting as the same as the others. So yeah, it's really hard to predict. But if I just had to, you know, just give you some general guidance in the right set of conditions, it's not uncommon to see a low to mid 40s sort of end result.
All right. Here's a question. Customer says, we mentioned anti-block during the session. This customer runs a high anti-fog application. And recently, while they didn't have Dyne issues, they did have a lamination appearance issue. Would you suggest higher watt density on high anti-fog loads, or have you used higher watt density on these types of films?
Well, we have, you know, the products that are used in, at least in our experience, some of the products that have been used there are products that are pretty receptive to corona. So we don't necessarily have to have a high watt density to do it. I think what in this particular instance, there's some details here basically that I have to ask, some application details. So maybe if this individual would check with me offline, I'd be happy to have a conversation with them and get a little more detail, and then I could maybe be a little more specific.
Would corona treating help with a closed cell PEEVA foam, either with a PSA or UV ink?
Don't get me started on foam, okay? I'm just kidding. Yeah, you can treat polypropylene, polyethylene foam. The magic there is thickness of the foam. How thick is the foam? How fast are you running? What are you trying to accomplish? There's a lot of questions when you get into foam applications that probably aren't suitable for this venue right now. But the person who asked that question is a great question. I have a lot of information for you. So again, if you want to reach offline, I can be happy to talk to you about that.
And that would go with another person with a similar question, wanting to find out why there may sometimes be holes after treatment with foams.
Well, that actually is very simple. So I want you guys to think about this. What's a corona treater? What is corona? What is it?
Ionized air.
Thank you. Corona's ionized air, and if you look at what foam is, what's foam? It's basically all air. Whether it's closed cell or open cell, you got a lot of air in there. So of course, if it's open cell foam and it's only like a 2 or 4 pound foam, and you turn a corona treater on, you get this discharge, and it's ionizing the air that's in the foam. And because the foam has really zero electrical insulating property, if you get any dirt or debris on the electrode, it's going to throw an arc, and the arc's going to go right to ground. The corona goes where? Right? We said the corona goes to the path of least electrical resistance. And that was a key takeaway I wanted you guys to remember. So when that happens and you're running foam through there, you're going to get a pinhole in the foam. So a challenge with corona treaters is when you run thin gauge foam, and particularly open cell foam, and if you're not mindful of cleanliness, how much power you're applying and so forth, you can get some pinholes in foam. So you really have to be, the process window when running that product is real tight.
We have someone trying to treat and print on both sides of the web, then thermally seal the web to itself to create a sleeve. Is it possible with two-sided treatment?
I don't know. We've had some thermal lamination applications in the past. They've been very specific with very specific product details. So I can tell you that in theory, it could work. But there, again, devil's in the details here, so we'd have to have a dialogue about sort of what your expectations are, what the end use is, that sort of thing, and then we might be able to give you a little more information.
Is there a level of corona treatment that can actually accelerate the additive migration?
I'm not aware of. We haven't done a study of that or anything, so I can't say there isn't, but I don't know. It's a good question.
Someone has had an experience where a steel electrode boosted a polypropylene film faster than a ceramic electrode. Could you speak towards that?
Yep, not a surprise there. And why is that? That's a great question. The reason for that is if you look at both discharge sometimes, look at a ceramic electrode discharge, look at a metal electrode discharge. Make sure that both the discharges, the gap's the same in both cases, using the same power supply. When you look at them visually, you will see that the ceramic electrode has less filaments in it, little electric lightning bolt looking things, less filaments than a metal electrode. Metal electrodes will typically have a lot more jagged little lightning bolts that come off them. Now let's look at an example practically here. We'll go back to our foam example. So in that instance, if I ran that foam with a metal electrode and all the little lightning bolts, that would be bad, right? The foam would pinhole and you'd have a product you wouldn't be happy with. So the foam, in that case, is not happy with that electrode. Now let's look at polypropylene film. Polypropylene film is very crystalline in nature, so it's got a very tough surface. Sometimes in order to get through that surface and get an effect, you need that sort of harsh discharge in order to be successful. So it's not uncommon to see metal electrodes in certain applications, depending on what the film is, be more successful than a ceramic application. So again, the application always drives the equipment, friends, always, right? So depending on what the material is, and that's why we ask you all these questions. That's why when you talk to Todd or talk to myself or talk to any of your other friends in the corona industry, they'll always ask you these questions. What's the film? How wide? What speed? So on and so forth. And it's not because we're trying to be nosy. We need to know these application details so we can make sure that the corona system is set up appropriately for what you want to do.
All right, we've got time for a couple more questions. I'm going to put a couple of these together because they all have to do with humidity. Questions regarding air humidity and corona effectiveness in the winter and summer. Another person who is in a dry part of the U.S., is there any effect there? And then also if you're, it looks like this one's treating paper, does moisture in paper affect the level of treat?
Well, remember, folks, what we talked about earlier. What was the key takeaway here? Corona always goes to the path of least electrical resistance. What's water? Is water conductive? You bet. So if in the summertime, if you have a lot of moisture, the corona's going to want to arc, and it may arc to ground and shut the treater off if it's bad enough. So it is conceivable that if you have a situation where you have a lot of humidity in the summertime, your maintenance load on that treater is going to go up in the summer. Cleanliness in the summer is going to be really important. You may actually have to have, or it may not have to have, but you may have to use a feature many of us have in our corona treaters, this wet start feature where you turn the treater on and it runs at a lower power setting for a prescribed period of time until things dry out, and then you can run at your normal output. So really, humidity, water, dirt, all that stuff has a negative impact relative to corona and really causes, again, your process window to tighten down, and it also causes you to spend more time on the maintenance end. For the guys on the other end of the scale, if you're in the desert in Arizona, you guys have the best deal ever. I've been out west and looked at some of our equipment that's literally 30 years old, and I'll tell you, that equipment looked great. It looked like it just got shipped, and that's because you don't have those troubles. You don't have corrosion, you don't have moisture causing high voltage arcing and all that kind of stuff that goes with it. So if you're in a dry climate, your maintenance load is a lot better, and likely you're not having the same issues with respect to the operating the treater as your compadre on the other end of the country that might have a humid condition that they're operating in.
All right, we've got time for one more question. If we did not get to your question, our team will reach out to you afterwards and address that. And certainly reach out to Todd and Tom if you have additional questions you'd like to take up offline. This person was running a 10-station UV flexo press application. Corona treating before the first station, Dyne level was high, but it dropped by the end of the press, station number 10. Is this logical? What's the cause? How could it be avoided?
Well, it could be logical. So again, when we're measuring the surface centers, remember, the corona is only treating the top couple angstroms of that film. It's not going through the film. So as this film is conveyed and it's hitting all these various idler rolls as it's going along, it's conceivable that some of those idler rolls, A, either aren't turning at line speed, right? They're dragging. B, some of the rolls have a contamination on them, which could transfer onto the web. So if you take A and B and you go to C and say, well, now I'm going to measure the Dyne level after all these stations, that you could see an instance where the Dyne level isn't where you want it to be, or at least an area of the web has got a lower Dyne level as a result of maybe the rolls aren't turning at speed, maybe there's a contamination that got on during the process of the film being conveyed. So it is possible. Now I will say again, it's not common. It doesn't happen very often, but it is common, or not common. It is possible. It could happen.
All right. Once again, I'd like to thank our audience today. Hopefully you've enjoyed today's presentation. If you have ideas for future webinar topics for us, please let us know. And if you'd like to drop us a note as well as to what you liked about the webinar and what you'd like to see in the future, we'd certainly appreciate that as well. That will conclude today's webinar. Thank you for joining us.